my pleasure to introduce our speaker when I find my appropriate crib sheet. There we are. It gives me great pleasure to introduce Mark Neal to give our talk this evening. Mark was a member of the Department of Computer Science in Aberystwyth until about 4 years ago, and he now runs his own company, Stemtech, I guess that's how you pronounce that, Limited, and he specializes in making custom-built hardware, firmware, and software for research organizations in academia and industry. And in particular, he builds lots of sensors and things like that. And so this evening, he's going to talk about computing in cold places, ice cubes, fjords, and hand warmers. So over to you. Oh, sorry, before Mark starts, could I ask everybody please to remain muted and turn off your video during the talk so that we don't get distracted by animals and so forth that might be in the background. And if you have any questions, please put them in the chat, and Neil and I will try to deal with them at the end of the talk. So over to you, Mark.
Thanks, Fred. 4 years seems like a long time ago. Doesn't feel like that long, really, but yeah, Stemtech seemed like a really good name for the company when we first set it up. But I do spend an awful lot of time spelling it to people on the phone and having people attempting to pronounce it and then giving up halfway through and various things. Right, so I think this talk was invited probably mainly on the strength of photos that I posted to Facebook of exciting looking cold places and bits of snow and icebergs and things like that. So I have got a fair few of those sort of pictures in here, but hopefully there's enough technical content that you won't get completely fed up with it. I hate doing things online because I actually quite like being interrupted while we go along, but I guess that's not realistic here. So we'll just have to put up with me talking at you for a long time, and then we can do some questions at the end if there's stuff you want to talk about. Okay, so I can get my, yeah, so I thought before I dive straight in, I'd just say what sort of stuff do I actually like doing, and why do I get involved with these sorts of things? And I guess probably top of the list is that I really enjoy working in interdisciplinary and or multidisciplinary teams. I like working with people who have a different agenda from what I have. I like working with people who have problems and knowledge in areas which extends what I know about, challenges me to think through different aspects of what I'm doing in their terms, and to try to make systems that fit in realistically to the problems that they're trying to solve, and to the workflows that they need, and in the locations that they need to do it in. On top of that, things that are rooted in the physical world. I was into robotics and that kind of thing for a long time, and I like systems that involve being out in I mean, I like challenging environments, but it's not just that. I like the aspect of building systems to actually achieve things that affect physical objects around you, or measure physical objects around you. I don't really like living in the sort of classic computer scientist build a world and then do research within it. I'm kind of something in my head which makes me want to do stuff that has a real world root. And that sort of led me away from I was never a pure computer scientist, who am I kidding? But that led me away from programming more towards electronics and hardware over the years, and that's why I ended up doing lots of robotics and that kind of thing. So the company has kind of drifted further and further into that setting. So it started out mainly building sensor systems and stuff like that, which is what Fred mentioned. But over the last couple of years, particularly, doing a lot more work on instrumenting farm machinery and building sort of semi-robotic test rigs and things like that, for pieces of specialist lab equipment for people, which is really good fun. It ends up being a lot of low-level control system stuff, quite a lot of electronics design and bits of hardware, which really appeals to me. and then I'm rapidly offloading the software side of things onto people that I'm paying to do it for me. Partly because I don't enjoy it, and partly because I'm not really that good at it, and lots of other people are better at it than I am. I like also dealing with systems that are on the edge of all sorts of things. I like dealing with trying to build things at very low cost. It's kind of fun trying to eke as much as you can out of low cost bits of hardware, and to try to use components, systems, whatever, up to the best that they're available to get as much as you can out of them. And that might be because you're pushing their resolution or the environment they'll work in, or any number of things. And that means that inevitably I build stuff that doesn't work sometimes. And I'm happy with that. That's okay. And I do try to be upfront with all the customers and all the people that I work with. If I think that we're in a situation where that's possible, then I'll give them the options. Do you want to try and make 50 of these for the budget that you have, to allow you to get a much larger number of measurements, or would you like me to build you 5 that you're pretty much guaranteed to work? And then we have that discussion up front, and I enjoy that side of it. It's fun, it's interesting, and it means you have to push yourself and the systems that you're building right to the edge. It does irritate people sometimes, but as long as they know what the score is, I can live with that. I also really like interesting places and environments. I've done lots of traveling over the years and been to various places, and I like to meet fun people who have very different lifestyles and different cultures. I like to experience the wildlife and the areas that they live in, and so these are all kind of motivations which push me into doing things that might appear to be a little bit ridiculous sometimes. I promise, I had to put a couple of pictures in. So possibly the cutest little bird I've ever seen on the left-hand side there. Apparently is a Horniman's redpoll, and I love the fact that he's got a single snowflake sitting on top of his little red head. And then there's a big scruffy raven. Good population of ravens in Greenland. If you want to find birds, you're pretty much always going to see big black ones flying around the place. And then tiny little redpolls. So what was the project? What was the reason that I ended up in Greenland? Well, I've been out there. I went out there with university a couple of times on projects that were collaborative with a bunch of people from Aberystwyth, but also people from other places. And one person that I was involved with quite a lot was a guy called Nolwenn Schulze, who I won't talk about a huge amount, but he certainly gets an acknowledgement at the end. And he did a PhD at Aberystwyth, and he spent a couple of years living on a boat frozen into the ice just by one of the glaciers that we went out and surveyed with him, and taking various readings throughout the whole year, right through the middle of the winter, going out and drilling holes in the ice, lowering instruments in, that kind of stuff. So he's kind of he's a good friend. We, as a family, we went out on holiday to visit him on his boat out in Greenland, and that was great fun. But also he's a very skilled researcher, and he has a lot of experience working in these sorts of areas. And some of the trips that I've been on to Greenland have been, shall we say, challenging in terms of organisation and the people that were on them and running them. And Nolwenn was not one of those people. Nolwenn was one of those people who could organise stuff, and you did trust not to do stupid things and take ridiculous risks. But also he was, keen to do the best science that he could. So we worked with. I've worked with him on various projects, and most of the time, what I've done with him has been based around multi-beam sonar. So these are pieces of fairly high precision sonar equipment designed for mapping seabeds, and to build 3D models of what the beds of the ocean look like. And there are lots of reasons for this. I'll talk a little bit more about that in a second. There are lots of reasons for doing that, but it gets quite challenging quite quickly, because you're taking these pieces of kit which are designed to be mounted on relatively stable boats with a good power supply, lots of fairly high-tech equipment around them, GPS coverage, compasses, all that kind of stuff. And when you try to integrate those into the sorts of systems that are a little bit on the edge, the kinds of things that I like doing and that he wanted to do, you put them into small footprint, small systems with small amounts of power availability, and in this case underwater, then things like GPS just don't work anymore. And because you're very high latitudes, you can't really rely on the magnetic field of the Earth because it's not very useful. So compasses aren't a lot of use up there. So we're kind of pushing all these things to the edge of what they were able to do, and trying to keep the costs down for the customer, who in this case, the ultimate customer was a guy from University of California, Irvine, and he's also part of NASA at JPL. So he had a limited budget. He knew what he wanted to do. And then Nolwenn subcontracted to me to build some of the parts of the system for him. So yeah, we had a fairly decent, well, a very decent quality multi-beam sonar system, 117 kilohertz, which is relatively low frequency. It's not the lowest. You can get systems that go down to about 50 kilohertz, and they'll have a range of maybe 800 or 1,000 meters. The 117 kilohertz stuff has a realistic range of about 500 meters. Yeah, so then we had some fairly fancy attitude and position measurement stuff. I'll talk a bit more about that in a moment. And the idea was to be able to survey deep water fields in areas that you can't get a boat to, which basically means, but where in Greenland, that's you can't get a boat to them because they're covered in ice. They're covered in icebergs or sea ice or whatever it is. And for various parts of the coastline, they just never clear. You never get a period of long enough to be able to get a boat in there, do your surveying, cover enough of the seabed for it to be useful. So what we were trying to do was to build a system that could be deployed through the ice with this multi-beam sonar system, and allow us to build 3D models of the underlying beds of the fields. Yeah, a horrible collage of pictures. Sorry about that, but it gives you the idea. So the little black, I don't know if you can see my cursor, but the little black blob in the lower left corner of the screen, that's the island of Greenland. And then the little square box is the area that's in this bigger box here. So basically we're on the west coast of Greenland, not that far north. I mean, it's far enough north that you get 24-hour daylight and it gets blooming cold in the winter. And the little red dots are all settlements, and it makes it look like it's really busy and there are loads of people living there. Well, it's not like that. So Ilulissat, which is the place that we were based at, is this one with a little picture of an airplane and an airfield about a third of the way up, with a square box by it. Ilulissat has a population, I think it's about 4,000 people or something. It's the third biggest town in Greenland, and the total population of Greenland is about 30,000 or something like that. Most of these other little dots are really very small, so that they'll have a few tens of people living in a lot of the villages. 10, 20, 50, maybe 100 people living in a place. So it is pretty remote. There are essentially no roads. There are roads in Ilulissat that go all the way to the airport, which is I think 3 kilometers out of town. So if you tried really hard, you could probably drive about 15 kilometers if you drove around town all day without driving on the same road twice. People don't get around in cars. Basically, they all have cars, which is a bit crazy, but they don't really serve much purpose other than stopping you getting wet when you go into the shops. So how do people get around? Well, when the sea is frozen, then you can actually use vehicles if you want to. You can use dog sledges, and there still are quite a lot of dog sledges around. Skidoos, which are also very popular, but actually can be a bit of a liability because they can get very stuck very quickly. And then the only other alternative, for instance, is if the ocean's clear in the summer and there's not too much ice around, then you can obviously use boats to travel longer distances, and they do. There are a lot of boats and a lot of fishing goes on, but you can also drive around the top of the ice. But really, if you really want to definitely get somewhere, then it's helicopters and airplanes, and that's how you're going to move around. So there are quite a lot of constraints on traveling about the place. So just to the south of Ilulissat, there's a field that goes in, and this is euphemistically and lovingly painted in blue on the picture on the left-hand side. It is almost never water. It is almost always full of ice, and that's what this satellite image, Sentinel satellite image, is on the right-hand side, the big image. You can see Ilulissat's marked up in the about 2/3 of the way up on the left-hand side. And then this field here is Jakobshavn field, which is is known as the ice field because it's pretty much always full of ice, and it produces huge numbers of icebergs and massive amounts of ice that come from the main ice sheet. So and this is a particular interest, this field, because it's one of, I think, 3 known fields that actually extend through into the center of the ice cap. So the ice cap on Greenland is several miles thick, and in the center, the weight of that ice cap's pushed the Earth's surface down to significantly below sea level. So if you were to remove all the ice instantaneously from Greenland now, there would be an ocean in the middle of the Greenland mass, and that would be connected to the sea by 2 or 3 fields, one of which is this field here. So the glaciologists are really interested in knowing about this field because it's very deep, and it connects to that low point in the center of Greenland. So the last 3 or 4 years, Nolwenn has been, Eric, the guy who funds these projects, has a boat based in Ilulissat, and he's been employing Nolwenn to try to get into this field with a sonar system mounted on the boat to build some 3D models. And last year, Nolwenn did manage to get in, and he surveyed a part of the north coast of this field, just beyond the field that goes out to the north here. He managed to get to about here, but he didn't manage to cover the whole width of the field because it was still full of icebergs. So they've been trying to fill in the gaps on this model for quite a long time, and that's where this project came from. Okay, so what we're mainly doing is integrating bits of OEM kits from various companies, inertial measurement units, communication systems, that kind of thing. There are a few sort of key components on this slide. So down the bottom left here, the yellow things are the sonar transducers. That particular model, I've got embarrassingly few pictures of this, of the actual bits of kit, which is, I'm not very good at recording these as I go along. This particular kit here is I think a 234 kilohertz, so they're significantly smaller. The transducers that we were using are about twice the size of this with respect to the connectors and everything. So they're pretty chunky. They're about 0.5 meter long, 200 mil wide, and they weigh several kilos. They're pretty hefty lumps of stuff. The PCB at the top here, the green thing with the 2 cutouts, is the main power and communications board that drives the actual sonar transducers through various other bits of kit. But that's kind of the heart of the system that we're working with, and that has a Raspberry Pi compute module built in, and a network switch and various other things. And then we use these StarTech VDSL extenders to run the signals up and down the main tether. And I'll talk to you a little bit more about the geometry of how the whole thing fits together in a second. And at the bottom here, this is a very fancy looking inertial measurement unit. So this is working out the attitude and orientation of the device while it's in the water, to try and be able to georeference the data that you're getting back from the sonar. So to be able to work out exactly where you are in 3D and what direction you're pointing in, to know how to process the signals that are coming back from your sonar system. And then on the right hand side, you just have the thrusters, which are used to control the attitude of the device as it goes round. I'll describe that in a second. So the main problems, number one is, how do you get through the ice? So you know that these fields, which can be up to about 1,000 meters deep, have ice floating around the top. That can be sea ice, which is formed through the winter if there's not too much wave action and there's not too much motion of other ice through there. You can get saltwater ice, which can grow up to getting on for 1 meter thick, very stable, very flat, and relatively easy to cut through because it's nice and contiguous. So you're going to have to make some holes somehow if you want to get through to the water underneath. How are you going to control your sonar scanning and the attitude of your scanner system? What's going to get done underwater? And there are huge numbers of possibilities for how you could go about doing that. You could put through some sort of vehicle or an autonomous underwater vehicle that has the system mounted to it, but chucking autonomous underwater vehicles through a hole in the ice and expecting to get them back at the end of the day is a pretty high risk activity. and they do get lost with monotonous regularity. So having a bit of string of some kind attached to whatever device you're putting through the hole is a pretty big advantage, because if everything goes really wrong, you can pull the piece of string and get it back again. Once you're through, well, yeah, so if you've worked out a way of controlling the attitude and doing your scanning and how you're going to get through the ice, how are you actually going to physically get to where you want to make the hole through the ice? These places, as I said, you can't get on a 27 bus. You're going to have to figure out some way of getting to where you want to be, and that's not a trivial problem, and has all sorts of knock-ons for the specs for your equipment, depending on how you're going to get there. And then there's just all the really boring infrastructure stuff. Where are you going to get your cup of tea and your sandwich? How are you going to charge your batteries? That kind of stuff. And it sounds trivial, but actually becomes a really major problem when you try and work in that sort of environment. So what did we settle on? Well, the initial design spec from Eric, the guy from UC Irvine, was to be able to work on a glacier right in the northwest of Greenland called Petermann, and to be able to deploy this thing through up to 60 meters of ice. So basically the Petermann Glacier is a glacier that flows out from the central ice sheet, and then it has a big tongue that floats out on the water, and they don't really know how thick it is because they've only measured it in one or two places a long time ago. But their estimates are that it's between 30 and 60 meters thick. At least this is what we were told. And the idea was that to drill through 60 meters of ice, essentially you use a hot water lance. It's basically like a hot water pressure washer. You can make holes of whatever size you want to, depending on how much fuel you can carry there to power these things. If you're working on sea ice, which only tends to be a meter or whatever thick, then you can use a handheld ice auger, which is basically a motor on top of a big screw, and you just drill a hole through the ice. And this is the kind of thing that you see fishermen in Canada or Russia or Finland or whatever it is, drilling holes through ice to drop their fishing lines through. So those were kind of the two methods that we designed around. As it turns out, we didn't go to Petermann because of various things, one of which was the Swiss team that were supposed to be going up there to make holes through the ice. They were the experts on the hot water drilling who were going to be part of this project. They lost one of their scientists in an accident on the Greenland ice sheet earlier in the year, or last year actually, which had huge repercussions for what they were willing to do and how they were willing to do it. And they have a major health and safety drive on at the moment to try to ensure that sort of thing doesn't happen again. So we were all pretty paranoid about safety, as you would expect. So we're going to drill a hole through the ice, either using an ice auger if we're on nice friendly sea ice, or we're going to use hot water drilling if we're going through something thicker. And we settled on 250 millimeters as a diameter for the hole, because that was constraint. The main constraint was the size of the sonar transducers. The sonar transducers are just over 200 millimeters wide, and you need a certain amount of offset from the center line of the instrument. So you basically you can't really get away with less than 250 millimeters to use that sort of sonar kit. The transducers, so there are two sonar transducers, two of those big yellow bricks, and the idea was to have them facing slightly downwards and slightly back to back, so that you could then rotate the whole system around and build up a sort of a dome of data, if you like, facing downwards, which would cover the seabed below you. We're going to use thrusters for rotation, so you have something hanging in the water column with these two transducers bolted to it and whatever supporting kit you need inside. And then you have thrusters on the ends of this thing that spin it around in a nice controlled way to allow you to build up a 3D model. And this is kind of the same principle that modern 3D laser scanners use. Terrestrial laser scanners, they have a laser that's spinning around, and then the whole instrument rotates around, so you get a kind of 360-degree view of the world. Getting us to where we wanted to be, basically, skidoo and helicopter, they were the two options. So the skidoos are quite nice because you can put big trailer full of stuff on the back, and you have quite a lot of pulling power, and you can go quite a long way and pretty quickly if you want to. But they have the really big advantage is they're cheap. You can get a man with a skidoo and a few gallons of petrol, and you can do an awful lot of work in a day. Unfortunately, the ice on the main field, the bit that we were really interested in, you cannot get a skidoo on. It's just too broken up and too unreliable. So basically, it's extremely hard to get into those areas, particularly at the time of year that we were there when the ice had started to break up and start to move around. So to get to those places they were really interested in, helicopter was pretty much the only choice. Okay, so embarrassingly, this is the only sort of decent picture I've got of the whole instrument. So what you see there, the big yellow thing that's facing us on the right-hand side is one of the sonar transducers. Like I say, it's like 550 millimeters long and about 200 and something wide, and it's about 100 deep. And then you have two of those offset angles facing downwards at around about 45 degrees. Actually, not quite. I think I can't remember. Nolan worked out the sums to get the best coverage. So the angles were chosen quite carefully. They're mounted to a custom-built aluminium frame, and that center aluminium tube became known as the bottle. Contains all of the electronics, batteries, control system, everything inside there. We had Nolan and I put together the system that's inside there between us. I was supposed to go and visit him to do some lake testing. Of course, that didn't happen because of COVID. So we did the whole thing by Zoom and posting each other bits of equipment. So it was pretty terrifying because the first time it ever went in the water was when we were in Greenland. So we'd had absolutely no guarantees that any of the stuff that we put together was going to work at all. Amazingly, it did. So there were a few beers drunk the first night that it actually worked. So that bottle is rated. It's about, I think it's about 18 millimeters thick aluminium, and designed to go down to about 700 or 800 meters of water, which is about 70 or 80 bar, which is pretty high pressure. The way that you do these things, it's all sealed with O-rings and things like that. So you assemble it and then you pump the air, as much of the air out of it as you can, so that the O-rings are sucked into the position that they're going to stay in. And then you try really hard not to take the thing apart ever again. So once we were in Greenland, essentially there was a really big incentive not to dismantle it, because putting it back together would have been hugely risky, because we didn't have a nice clean workshop to do it in. So yeah, we've got the two transducers, we've got all the electronics in the center, which includes the inertial measurement unit and the Raspberry Pi and GPS receivers and various other bits and pieces. And then on the ends, the two grey things are 3D printed cowlings, and the big holes in them have the thrusters inside. So the idea is that this thing hangs horizontally in the attitude it's in that picture, in the water column, hanging from a tether which goes all the way up to the surface, which is what that big coil of cable on the left is. It's a tether spool, and we have a petrol-powered winch. So it's hanging from that tether vertically and horizontally in the water column, and then we use the thrusters to rotate the system around very slowly. And the idea was to do 1 degree per second for my control system to rotate the system at 1 degree per second, so that we got really nice dense coverage of the seabed. And we would do a full 360 rotation, which meant we got 2 scans of every part of the seabed, one from each transducer, and that would help us to iron out any problems with the calibration and the angles of the two systems, any changes in orientation, attitude, that sort of stuff. The cable that comes up to the surface, 600, I think it's 650 meters of it or something, I can't remember exactly, but it's that sort of order, ends up being blooming heavy, but also means that you have to work out what you're going to do with communications. And we opted for VDSL, so it's just copper conductors, 8 copper conductors in 4 pairs, 1 pair of which is used for VDSL, and then I'll talk a little bit more about what the other ones are a bit later. So the system there is hanging horizontally. We've made a 250 millimeter wide hole in the ice, so it has to go through endways, which means that it can't be horizontal when it goes through the hole. So how are we going to deal with that? And what we came up with is a fairly complicated system of bits of string and solenoid releases. They are pretty fancy string. It's all bits of Kevlar, and the tether cable is rated at pretty high strength and that sort of stuff. And I'll run through how that works in a second. So you can see it's kind of a mixture of super high tech and horribly crude. We've got some pretty high tech stuff going on in the instrument itself, and then we've got a horrible crude drum full of cable and a tripod and a petrol powered winch to hoik the thing up and down. And that's sort of fairly typical of the stuff that I build, I think, and Nolwenn. But we generally make stuff that works. So this is one of the solenoid releases. Can I go back up? Yes, I can. So there's a solenoid release on each end. You can see the white blob where the white rope joins the grey casing on the left-hand end. There's a little white cylinder below that, and this is a solenoid. It's not the one in the next slide, but it's basically withdrawing it, pulls a pin out, which allows a hook to unhook and releases that white rope from the left-hand end. And then on the right-hand end, you can see the end of the hook, which is on the next slide, poking out, and that's used to hold it around the main cable during lowering. So this is basically it's a 15 quid RS solenoid, 30-watt solenoid that's been stripped down, coated in epoxy and various potting compounds in about a 20-step process to try and waterproof the thing. And it did actually work pretty well, and they were still working when we'd finished. And what it does is to pull the pin downwards, and this is that spinnaker release hook that's been modified, welded up in stainless, and it allows that top loop to open like a jaw, and that releases the rope that's held through that top circle. So that's one of the releases. I haven't got a picture of the other release because I wasn't organised enough. Apologies. So how does it work? Essentially, you find your lovely bit of sea ice, you drill a hole through it, and then we set up a tripod, which is what the black triangle is supposed to represent in that first image on the surface. We have the winch attached to the sea ice by ice screws, which if any of you have ever been ice climbing, you'll know about. They're just aluminium screws that you screw into the ice. And then you lower the device through that hole into the water. Once it's into the water, it's hanging vertically with all both of the clips still attached. One of the clip that I showed you on the previous screen, the release that I showed you on the previous screen, is attached to the end of to one end of the timb of the instrument, and that's looped around the main lowering line. So that holds the whole thing vertically, hanging on the end of the tether cable. Once you've lowered it down to depth, this was the plan anyway. Once you've lowered it down to depth vertically, you then release that release on one end, and that allows the instrument to fall and hang vertically from the bridle, the Y-shaped bridle. At that point, we then turn on the sonar, turn on my control system, and the thrusters then very slowly rotate the thing around by 360, possibly 720 if we're feeling like we've got the time to do it, to ensure that we've got plenty of good data. And then once you've finished your scan, you release the other end, which allows the whole instrument to fall down and become vertical again, and then you can recover it back to the surface and pull it back up through your hole. And actually it worked. Like I say, we'd only ever tested it in air. We'd never tested it in the water before, and the first time we deployed it, we did it off the side of a boat into the harbour, just at 5 meters of depth, and it all worked pretty much flawlessly first time. In fact, it worked perfectly. So yeah, that was a fantastic relief, having spent the best part of a year building this thing. So this all looks lovely and looks really believable, and this was how it was all going to work, and that's great, except that sea ice is never quite like that. Sea ice is usually more like this, and particularly in the field where you've got the glacier depositing bits of iceberg into the water all the time. It's actually like walking around on top of a gin and tonic that's been partially refrozen, only some of the ice cubes are 200 meters across and some of them are 20 centimeters across, and you're trying to set your equipment up on top of that, and you drill a hole through or you think through the ice, and your hole, of course, fills up with all the bits of ice that you've created with your drill, plus other bits of ice come floating up from underneath. And you optimistically lower your machine into the hole, and it goes down 2 meters, and then it stops going down because actually there's another piece of ice poking out somewhere underwater. And then you poke around with a big aluminium pipe and you try and shove it down, and it all gets very, very tedious very quickly and incredibly hard work. And you end up with wet feet and wet tools, and you drop stuff in and the ice cubes move around and your tripod falls over, and it's all deeply not very entertaining at all. But, well, I lie, it is entertaining, but it can turn into something of a risky activity and can get pretty unpleasant. And I'll show you some pictures of that a bit later on, what the surface looked like that we're working on. If we were doing this, ironically, I think if we were doing this on the 60-meter thick or 30-meter thick ice shelf, actually it would probably be easier, in that you would be boring a hole through a very large slab of ice that's not broken, it's contiguous. You would know when you came out the bottom. Sure, there's the risk that you might have the odd lump and things hanging out the bottom, but I suspect that the actual deployment process would be a lot easier once you drilled the hole. And using it on these broken bits of ice on the fields was trickier than it would have been in a normal environment. Okay, so that's what we were trying to do. So we were trying to drop our instrument down into kilometre deep water. We only have about 500 meters of range from the scanner, so we need to be able to get the thing ideally 600-700 meters down on the end of a cable. And there's a whole bunch of other infrastructure that's sort of tied up with that. Batteries, power, generators, petrol, all that kind of stuff needs thinking about and needs working into the system. You're throwing things in and out of helicopters or on skidoos. And if you're on a skidoo, then things have to be packed pretty carefully because it's not a smooth ride. You're doing 30 miles an hour and jumping off things and bashing over lumps and that kind of stuff. So everything has to be packed pretty carefully. Same applies in a helicopter. Only, of course, the pilot won't go anywhere unless everything's completely nailed down and tied down. He's convinced that everything's absolutely safe. So there's quite a lot of weight and effort in packing materials. And the basic rule is that everything's too heavy. The instrument itself weighed. I never managed to get a figure out of Nolwenn. I don't think he was sort of too embarrassed to say, but it was between 65 and 70 kilos. The winch drum itself, with just the cable on it, was about 65 kilos as well. And you've got to unload and load all this stuff each time you're setting the system up. So yeah, making stuff lighter we made a serious effort to make stuff lighter as we went along and as we went through the design. But still, it's incredibly hard to get that sort of equipment to be both robust and lightweight and not cost an arm and a leg. So deployment and recovery, we're unloading from either the helicopter or the skidoo. We set everything up. We get a GPS and IMU fix with the instrument on the surface. In the meantime, while that's happening, we drill the hole in the ice, set up the tripod, lower the system down disconnect the GPS and all that kind of stuff, lower the system down, set my rotation stuff off, perform the scan, do a bit of quality control on the data, repeat things if necessary, then release the second to rotate the instrument back to vertical again and pull it back out the hole. You then break everything down, repack it all into boxes, reload it back onto the helicopter or the skidoo, and head off for your next hole. And that all sounds quite good in principle. In practice, we never managed to turn around a hole in less than about an hour and 45 minutes, including transit time with the helicopter and skidoo, which means that you're basically spending 2 hours to do each hole. And in a working day, you can possibly fit in 5 or 6 of those if you don't mind working really hard. So yeah, to cover something the size of that field is about 30-something kilometers long by about 5 kilometers wide. So if you're trying to cover the entire field with that, you can imagine that you've got a 500-meter diameter circle. It takes an awful lot of load to fill it up. So we were pretty carefully targeting which areas we were gonna try and tackle. So here's some views of what it's like on the ice. The top right-hand picture there with the 2 skidoos and the complete setup, that was heaven. That was a really quite nice cold day, so everything was still frozen, not too much water flapping around the place. It was about, I don't know, -10, -15, something like that. Sunshine, flat calm. That was I think the second hole we did on the very first day, and we were feeling pretty pleased with ourselves because everything worked. We tested it on the boat the day before. We'd gone out with the skidoos. We hadn't broken anything. It all worked. We got some really nice data, and we were all feeling very cheerful. Which on the left-hand side of the screen is the first hole that we did from the helicopter. So we're flying around over this field looking for likely places to land. The helicopter pilot's never really done this sort of thing before, so he says, "Oh yeah, let's pick a nice flat place where we can deal with this stuff. I'm not going to land because I don't trust that the ice is thick enough for the weight of the helicopter, but I'll put the helicopter down and basically hover with it on the ground." We unload all the kit. We drill our hole through our nice piece of sea ice. Everything's lovely, and it all works. And then Eric, who's the guy in the picture holding the GPS frame on the bottom right-hand side, says, "Well, okay, but that's fine, but these flat pieces of ice aren't where I need to be. There, we need to be on that lumpy stuff." So then you start pushing the boundaries a little bit, and that picture on the bottom right is much more representative of the places that we were working. That was actually a very nice day, that one as well. It was relatively calm and not too cold. But you are, balancing on top of ice cubes essentially, and try not to drop things and try not to fall in and get wet feet and that sort of stuff. This was a much less pleasant day. So this day was cold, slightly windy, and we were working on the ice cubes again, close up to the glacier. And it's just an indication of how you have to really trust the person who's flying the big red thing that's moving you around. So we would have to unload everything, and then when we were getting ready to leave, we'd have to put everything back in exactly the same positions it was that we'd unloaded it, and then he would land the helicopter back in between them. Well, not land, but hover the helicopter back with the skids touching down, and you'd have to reload that, which means you've got to trust this guy flying this thing with blades 3 or 4 feet above your head while he comes and lands back in the same position. It is quite unnerving. And he was a very good pilot, but it was windy, so hitting exactly the right spot and not kind of hovering over your heads and things was definitely a matter of faith. So, more infrastructure stuff. What's inside the TIMB, inside the instrument itself? There's a PI and network switch, and we have a VDSL modem that's connected to the tether inside the TIMB. We also have various other lines that are traveling up the main tether. There's a power line and a ground line. The power line is not actually any use for powering anything, but it allows you to know what the battery voltage is inside. Because you've got 600 meters of cable and a very small cross-section copper, you can't do any recharging or anything useful like that through it. So you've got power and ground. You've got the 2 VDSL lines, and then we have emergency overs for the solenoids on either end. I'll come back to that in a second. And a leak detection line. So if there's a leak in the system, there's a detector board inside which runs a buzzer and sends power up through the cable, which doesn't go through any of the computers or anything like that. So you've got some sort of warning if you've got a leak. It never went off, which was a huge relief, but it was something that we designed in from the beginning. Control and monitoring in the field, you power it on, you set up the GPS, and you wait for the GPS and the IMU to converge to nice solutions. We use a VDSL to Wi-Fi system inside the winch housing. So you have your VDSL connection inside the instrument, and you've got 600 meters of cable. And then you have another VDSL modem and a Wi-Fi access point built inside the winch housing. Had to be built inside the winch housing because we didn't want to have cables and stuff coming out of the winch housing rotating around. So you'd have had to have slip rings or connectors or stuff like that. So the whole thing was built into the center of the winch housing and allowed you to then connect a laptop to that in order to be able to connect to the systems that were running on the PI in the instrument at the bottom of the cable. That worked really well. Surprisingly, again, this was all stuff that we set up remotely and we'd never tested it in anger. There were some issues with Wi-Fi connectivity, and suspicion was that the The Wi-Fi access point didn't really like running when it was -20, and it was behaving slightly strangely. It never completely failed, though, unlike the laptops. We know that laptops and batteries don't really like the cold. Batteries, you know, if you've know anybody with an electric car or you've driven an electric car, it makes a massive difference when it's -5 than when it's 25 degrees. You know, you lose about 30% of your capacity. And obviously, it's the same battery technologies that you have in laptops and that kind of thing. So you lose capacity and the voltages drop significantly. The main battery in the instrument was a 30 amp hour 12-volt setup. It's 4 lithium titanate cells in series, and then 2 of those in parallel. The big blue cylindrical cells that people use for electric bicycles. And we thought about heating. We understood heating. We knew the batteries needed to be warmed up. So when I built the battery pack has silicone heated pads inside it. And there's also a 48-volt lithium polymer system in there for the releases, the solenoid releases, to make sure they have plenty of oomph. They only take a very short pulse of very high current to release, and that shares the preheat from the main TIM battery. The battery pack inside the winch is a 4 amp hour lithium ion pack, and we also have an external backup battery pack for that, so we can plug something into the center of the winch if we need to, into the charging port that's on there. And then the laptops that we took, so we had the main laptop was a Lenovo Yoga that Norman had used previously, and then I had Samsung Galaxy S, which is the thing I'm doing presentation on at the moment. We've been through lots of iterations with tough books and those kinds of things, and generally they're heavy, low performance, very expensive, and actually not that much more robust. If you know the usual modes of failure, you drop things on them, it doesn't necessarily protect them, or you drop them in seawater, they don't survive any longer really than normal laptops, because they're never quite as waterproof as you think they're going to be once they've been used for a little while. Yeah, so we carry fuel around for the winch engine. On the whole, we tried not to carry spare fuel because of weight in the helicopter. We had a petrol generator set, which we would love to have carried on the helicopter, but again, we didn't have the sufficient weight capacity or space inside the helicopter. And so carrying fuel around for the ski-doos was essential, but generally you try not to carry any more than you have to, because it's dangerous and takes up space and weight. The helicopter itself as a source of power is essentially a no-no. It's emergency only. You know, you would only be using power from the helicopter for making radio calls for people to come and collect you if you've done something really stupid. And then people provided a lot of energy for the system, carting stuff around, manually drilling holes when necessary, smashing ice up, that kind of thing. So we were pretty aware of power as an issue, always are when you're doing field work, and we had thought about battery temperatures and stuff like that up to a certain point. Couple more pictures. How are we doing for time? Oh, blimey. Apologies if I overrun. I blame your AGM. So the picture in the center is the main battery pack and electronics assembly that I put into the TIM instrument. And you can see there's a lot of extra gubbins on there. So there are balance circuits. The board in the center has relays for turning the main system on and off, and also for controlling the releases on the ends. It also has a supercapacitor backup power supply. That's what the orange capacitors are in the center, so that if everything goes off, they're charged and isolated from the main battery system. And you could completely disconnect the main battery system, and you had about 5 minutes to be able to activate the overrides for the 2 releases, because what you didn't want to do was to have the instrument hanging in the water column horizontally and not be able to get it back out through the hole that you dropped it in through if everything went wrong. So we had various overrides. We never had to use them. We did test them; they did work, but we never actually had to use them in anger. On the left-hand side is a picture of what's inside the center of the winch housing, which I don't have proper pictures of. Sorry, this is a PVC heavyweight PVC tube with batteries, and you can just see at the bottom there the VDSL modem poking out. Everything goes inside that, and then inside the main tube of the drum of the winch. On the right hand side, I'll talk about it more in a second, but we bought a very large number of these power banks from the only shop that sells electronic stuff in Ilulissat, much to the amusement of the locals. In fact, we bought everything they had in stock of those. So issues with power. The TIMB, the instrument was sometimes stored outdoors, so we didn't have an indoors workspace other than the kitchen in a small rented house in Ilulissat. We did have it in there sometimes, but it made the rest of life pretty unpleasant having a large, wet, cold thing parked on the floor in the way of the cooker. So the battery was often cold and required preheating before you could charge it, and that took some time. Took about 20 minutes for my heater system to get it up to a temperature that you would charge it at. And if you try and charge those lithium titanates below zero, then it massively affects their lifespan. So we had a thermostatically controlled heater system in there with some silicon heater pads that were built into the main battery pack. The winch was sometimes stored outside as well, covered in sort of semi-frozen salt water. You didn't really want it, and weighing 65 kilos, it's not really something you wanted to bring into the house if you didn't have to. Bizarrely, we hadn't thought about preheat for that. So we didn't have any preheat fitted for that. So when we wanted to charge it, we either had to just charge it and accept that we were destroying the battery slowly, or we had to bring it in the house and try and warm it up. The switch on that system was quite hard to see. It was tucked into the center hub of the winch for good reasons, because you didn't want it to get clouted as the winch was turning. And it was used frequently. Every time you put the instrument in or out of the water, you were turning that switch on and off, and powering off the Wi-Fi as much as you could to try and save battery and that kind of thing. And we're still not really sure, but we believe that it was accidentally switched on and off a few times. But it's hard to verify. We also had a separate winch backup battery because we were worried about the battery in the winch, and we knew that we could do something about it. So we had a separate power pack that could be plugged into the winch. But of course, it was never really needed because we had 4 amp hours of battery in the winch pack, and it only pulled about 250 milliamps when it was running. So we had 16 hours of battery or something, which was a lot more than we were ever going to use in the field, even with depletion with the cold. So inevitably, there came a time where, when we loaded the winch, unloaded the winch from the helicopter at the end of a day's work, it was left in the hangar at the airfield. And without realizing it, one of us had switched the winch on, we think, as it was left in the hangar. We got there the next morning, loaded everything up in the helicopter, flew out to the field, put everything in the water, everything was working fine, and then the Wi-Fi turned off, and we realized that the battery was flat in the winch. I'd forgotten to pick up the spare battery pack, which meant that somebody had to go in the helicopter back to the airfield, pick up this thing, bring it back. So we lost about 2 hours of time, and one complete data set, and about 250 kilos of helicopter fuel, and probably about $3,000 of airtime in the helicopter, all because somebody accidentally switched a switch on and I forgot to pick up the battery pack. So that's the sort of thing that really screwed things up. And we had the same problem with the cold laptop batteries as well. It caused a lot of aggravation and a lot of annoyance. Moving around with the helicopter is marginal at the best of times, because of the amount of weight that you can carry. And obviously every kilo of weight you put in the helicopter is fuel that they can't load. So you're trying very hard to minimize the amount of weight, which means things like batteries are key candidates for getting left behind. But it's an interesting trade-off between the two. Oh yeah, back to the making holes in the ice. We had a lovely ice auger, Canadian ice auger, which was a really nice piece of kit. An electric one. I've used a petrol one in the past and they're horrible. And the electric one's lovely because it doesn't make a horrible noise and you can turn it on and off at will. And it's sold with an excellent battery designed to work in the cold, made by Canadians who like to go and stand around at -20, drinking beer and catching fish. But unfortunately, shipping the batteries was not allowed. So the auger had been shipped out, ready for us, waiting in the warehouse in Ilulissat, but there were no batteries. So one of the jobs that we had to do when we got there was to find some way of powering this thing, because we couldn't do any work without the ice auger. And the solution was to go and buy 10 of those backup batteries that I showed you in the picture or two ago, take out the 3.7 volt lithium cells that were in there, series them all up, and we actually bought 11, and we made a 40 volt battery pack, which is what the auger was designed for, which was stuck together with gaffer tape and insulating tape and soldered into the main power supply, and it worked really well for about 2 days. At the end of the second day, I think it had a bit of a hard ride on the skidoo and developed a bit of a short and got a little bit smoky and a little bit exciting for a couple of minutes, but nothing that a little bath in the snow didn't sort out. Very fortunately, the last team member arrived the following day with batteries, which they brought in their hand luggage. And I find the whole thing slightly bizarre because you can fly around Greenland with a rifle and live ammunition and nobody bats an eyelid. But if you want to carry a small battery, everyone gets very upset. So that was, all good entertainment. Power source issues then. So the laptops tended to be carried around in the pelly case. A pelly case is just a big hard plastic case, like a briefcase-shaped thing. They're somewhat insulated because it has a foam lining, but there are no heaters, and they were in an unheated compartment when we were on the helicopters, and obviously on the skidoos they were just in the trailer on the back. It is absolutely impossible to run our survey kit without a laptop, so that was a pretty major key point of failure. And it all worked fine until it got cold. The Lenovo laptop we were based on, it would run and you'd be sitting there working away and it would say, I've got 60% of my battery left. And then once it got cold enough, it would just switch off. You would have no warning at all. And you would then have to significantly warm it up, which basically meant stuffing a laptop at -20 up your jumper for 10 minutes to warm it up and then take it out and get your next little bit of work done. Once we'd realized what was going on, we took to using chemical hand warmers, which we'd taken out as a safety thing anyway. We would fill the pelly case, we put 4 of these hand warmers in the pelly case with the laptop, and that would stay in there all day, and you'd have to replace them at lunchtime. And then when you were using it, because obviously there's not enough heat output from those to keep it warm whilst it was uncovered in low temperatures and wind and whatever, so whoever the operator was had a blanket over the head, which was actually very pleasant because it kept your fingers warm. And kept the wind off and kept the light out as well if it was very bright outside. And there were times with the Lenovo where if it wasn't predictable, but sometimes it would turn off and it just would refuse to turn on, even though you knew the battery was not flat. You could warm it up all you liked and it just wouldn't switch back on. You had to take it back, plug it back into a charger, and then it would turn back on again. But there's obviously something in the battery firmware that was protecting it. The screen brightness thing I thought was a thing of the past. There used to be a real problem with LCDs overheating and losing brightness in their screens, but this Samsung suffers from the same thing in the cold. And actually, the battery pack in this would run down to -20 fairly quickly. But once it got to that cold, the screen would be impossible to view. And I don't know what's failing in there, but I think it was something to do with the backlight. But you could just literally warm the screen up with your hand, and it would suddenly get brighter again and work again. But you're just getting up to the limits of all these things that aren't really designed for those sorts of environments. Mechanical damage, we had remarkably little, really, considering some of the things that we've experienced in the past. The work environment on proper sea ice was mostly very good, flat, predictable, easy to work, easy to drill, and you were accessing it from the skidoo, which took a bit of the pressure off, so you don't have a helicopter hovering while you're unloading things and that kind of stuff. It's just a little bit less stressful. On the broken glacial ice, it was really unpleasant. You are walking around on a mixture of ice cubes and saltwater slush. It was really not very nice at all. And even though, ironically, you're standing there, sometimes in water, accessing the water to get the instrument in was very difficult because it's loose. The ice was loose, so as soon as you drill a hole, you clear a hole, it would just, other bits of ice would float up into that hole and fill it up from underneath. Moving equipment around on a surface like that, once you'd managed to find a place where you could get the instrument into the water, carrying the equipment more than 5 or 10 meters was extremely difficult. And again, very unpleasant. And rotors running on and offload from a helicopter is really not a nice thing to do especially when it's cold. It's pretty hard to stay calm and not panic when things get blown away and stuff goes wrong. And you have to, and you do, but it's not a nice experience. We had relatively few breakages. We twisted the winch, got very twisted because it was designed to sit on flat sea ice. Wasn't really, and we were attaching it with screws to the ice. And when you were on the broken glacial ice, it was extremely hard to find somewhere flat. So that the steel was bashed flat at the end of every day to try and make it usable for the following day. We broke the main tether connector into the instrument got broken. We don't really know when, but it got the outer retaining ring got snapped. But we managed to bodge something together for that worked reliably afterwards. The end caps on the instrument were 3D printed in solid plastic, professionally by a company, not by us, in ABS, which is supposedly okay down to -20. They use it on skidoo housings and stuff like that, but those got pretty comprehensively mashed. We don't, again, that was over a wear and tear over a period. Part of that was dragging them through the holes in the ice, and part of it was being mounted and unmounted into the skidoo trailers and things like that. I think probably the biggest breakages were people, people getting cold, wet, tired, bruised, lifting stuff in and out of the helicopter. 60 kilos, and if the helicopter happens to be, sitting on top of an ice block, then you might be having to lift a 65 kilo winch drum up to more or less shoulder height between two of you in a very confined space, and it was pretty punishing on people. And Jae Hun, who's the PhD student who was with us, he didn't have a fantastic pair of boots. He had a perfectly respectable pair of decent snow boots, but actually working in that sort of environment, they had to be waterproof, and they weren't properly waterproof. So he got wet feet and got very cold a few times before we managed to find him some better boots. And that's actually probably the nastiest thing that happened when we were there, was him getting wet feet, because when it's that cold, it doesn't take very long at all to seriously mess up extremities. And the wear and tear on clothing was pretty outrageous as well. We lost things getting blown away by the helicopter, so we lost at least one hat. Eric lost a pair of gloves. We all ripped various bits of waterproof and thermal clothing, unloading and loading stuff from the helicopter mainly. So, and they sound, it sounds not that important, but actually it's a really big deal in that sort of environment. Not having proper waterproofing and proper warm clothing really does affect how well you perform and how well the whole system works. So lessons, they're not hugely to do with computing, really. Sorry, and I apologise for those of you who are hoping for a really proper, full-on geeky talk, but it's kind of not me, really. Big lessons are reduced opportunities for human error, and it's the same in so many technology-based things. Whether you're talking about cybersecurity or whatever it is, it's people are key to making these things work, and that's not necessarily to say they're weaknesses. They're opportunities as well, and we find ways to co-opt bits of equipment to do things they're not supposed to, and to solve problems. But also we create problems, and I think designing your equipment and designing how you're going to use your equipment are equally important in a fieldwork setting. So you're thinking about what the kit is and how it needs to work, but also thinking about how the people are going to have to use it, and how you're going to set it up, and how you're going to tear it down, how you're going to pack it, how you're going to carry it. All that kind of stuff is really important. We spent a lot of time rehearsing, and the helicopter pilots wouldn't take you anywhere or allow you to do anything where they knew they were going to have to do a rotors running offload without doing rehearsals. So we spent a lot of time picking bits of kit up, getting in and out of helicopters, clipping things in, checking on each other, that kind of stuff. And having a small flat team with no real seniority, or everybody was pretty much equal, worked really well eventually. But Jae Hun was there with Eric, was his supervisor, his PhD supervisor, and there was a little bit too much respect there at times, which made it less easy than it should have been. And we did get over that. In fact, the helicopter pilot told him to stop being so polite when things were going wrong. And we did get around that. But it was trying to make sure that people feel like they can say, oh, hang on a minute, you've done that wrong, we need to sort that out, is really useful. And everyone knows this in computing, attention to detail is just about everything, and that's down to all the little silly ergonomic things, where you put the switches, how easily you can see them, do they have an LED light in them that you can tell when they're on or off, can you tell by putting your finger in and feeling whether it's on or off, what kinds of connectors you're going to use, where are they going to go, have you got spares, can you repair them in the field, that sort of stuff. Clothing, just having waterproof boots, understanding the environment you're going to before you get there, and knowing what clothing you're going to need in that environment, and what bits of equipment you're going to need in that environment. And also with hindsight, and I only really thought about this, I mean, it had crossed my mind before, I only thought about writing this talk, is we knew about heating batteries, we knew it was a problem, and we took action for the main event. You know, we looked with the piece of equipment that we were building, the big sonar system, we thought we need to put heaters in here. Why didn't we do that for everything? Why didn't we plan ahead? You know, and I don't have a good answer for that, other than just not paying enough attention to the detail. We should have thought about putting a heater in the winch battery. We should have thought about having some way of keeping laptops warm, and we didn't. Don't underestimate the effect of conditions either on people and equipment. You know, it makes a really big difference when you've spent 4 hours bouncing onto a huge thing. When you get to the next place and it's the same again, you know, it's pretty hard to stay upbeat and keep working efficiently and effectively over that sort of time. But also, that was an effect of the helicopter pilots being braver than we thought they would be. Neither Noel or I expected the helicopter pilots to even think about putting us down on the broken ice in the middle of the field, where they did in the end. We were expecting to be working on the flat sea ice where it was nice big slabs. And of course, Eric was pushing for us to go to the places that he really wanted his data from, and we're happy to do it. But it was really the helicopter pilots' chutzpah bravery that put us into those positions. You know, and they were confident that it was safe, which is fine. But I think Nolan and I both overestimated the effect of the conditions would have on the helicopter pilots and what they'd be prepared to do. And the big thing is everything always gets pushed to the limit. Whatever you build, wherever you deploy it, however you use it, people will always take whatever you've built and try and do something just beyond what you intended it for. And we certainly did that. And we built the kit, and we knew what it was prepared to do, and we knew how we were supposed to be using it, and we still went beyond that sometimes. So I think that's, you know, it's obvious, but it's worth bearing in mind at every step of the way if you can, and to try and find ways to make those sorts of changes in how you use things not too damaging. So a few thanks. Thanks to Nolwenn, who you probably never met, lovely bloke. If you ever do come across him, buy him a beer. Eric Rigno from UC Irvine, who's the man who came up with all the money and ran the whole thing. Jay Hun, who liked tea made the English way, which I was very pleased about, gave me a fellow tea drinker while we were sitting in the hut repairing things. A guy called Jan Kortsen, who was the guy that we used in Ilulissat. If you ever go to Greenland and Ilulissat, I would thoroughly recommend getting him to take you out. He was a good laugh. And most of all, my family, for not being too cross that I went and had a lot of fun. Sorry, I went and worked really hard while they stayed at home during lockdown. And that's me done.
Well, thank you very much, Mark. That's fascinating talk. Quick question. I mean, did you get any useful data?
Yeah, I tried to persuade Eric and Nolwenn to give me some data to show you. Yes, we got some amazing data, and in particular at the head of the field, there were some interesting areas where the point where the glacier began to float had been measured over decades, and there was a lot of conjecture about whether this data was correct or not. They derive it from satellite radar imagery. And there's a line that was they call it the grounding line. So it's the point where the tongue of the glacier actually goes up and down with the tide. And there'd been a lot of talk in the literature about why this data was wrong. And basically they'd drawn this grounding line in a surprising place. And that was one of the places that we surveyed, was across the about 5 kilometers from the main face of the glacier. And we were expecting just deep way across, but actually we found a deep field about 2/3 of the way across. It was down to nearly 1,000 meters in some places. And then on one side where this ground line had been calculated to be, there was actually a huge underwater cliff that rose up to within about 60 meters of the surface. And the very, very first scan that we did, we were about 100 meters away from this cliff face, this vertical cliff face, which was incredibly lucky. So we managed to sort of color in that part of the map for the people who are trying to work out the glaciology side of things. So yeah, we did get some fantastic data, but I couldn't persuade him to give me it, and I think he's kind of saving it all up for his nature paper or something.
Okay. Jim Finnis points out in the chat that there are some very good views on Google Street View of that town in Greenland. So are there any quick questions? Okay. Question: have you compiled a proper playbook for any future expedition? It sounds like a lot of work was improvised.
Yeah, we do it every time we go and do it. We compile a playbook based on playbooks that we've written before, and we do a lot of planning. It may not sound like it, and this was actually probably the least organized one that we've done because of the lockdown thing and because of not being able to physically meet up and test equipment together. Yeah, so I mean, but we have equipment lists, we have orders of assembly and disassembly and repacking and that kind of stuff. So yeah, we do have playbooks and that kind of thing, but it's just very difficult to think of everything. And as I say, when you get out there, particularly when you're working for somebody else, they will move the goalposts instantaneously. When they see an opportunity to get some cool data, they will definitely change their minds all the time. Is there only one Tim? At the moment, there is only one Tim. Yeah, and if we'd lost it, we would have been stuffed.
Okay. Are there any? How many holes in total?
How many holes in total? I can't remember the number off the top of my head, but I think we did. It was between 30 and 40. I think it was a lot of holes. A lot of bouncing on ice cubes. I consumed more ibuprofen during that 2 weeks than I've taken for about the last 3 years, I think. Oh yeah, for off-world planets. That's a good thought. I think the idea of people. I mean, people have done the studies for these sorts of things, haven't they? For melting through exoplanet ice caps and things. Yeah, I don't know. I'll be involved. If you've got the money, I'll build it for you.
Even some of the satellites of Jupiter, I think, have got services. Yes.
Yeah.
Okay, I think we should call it a night. Thank you again, Mark. Fascinating talk, and thank you to everyone for attending.